Betelgeuse, the red supergiant star marking Orion's shoulder, has captivated astronomers and skywatchers for years with its unpredictable behavior. In late 2019 and early 2020, the star underwent a dramatic dimming event, dropping to about 40% of its normal brightness. Speculation exploded. Was this the precursor to a supernova? Had the star finally reached the end of its life? Billions of years of stellar evolution culminating in an imminent explosion visible from Earth in broad daylight. The dimming eventually reversed. Betelgeuse brightened back to normal levels. Analysis revealed the dimming was caused by a massive ejection of material that condensed into dust, temporarily blocking our view of the star's photosphere. Not a supernova precursor, just an unusually large dust cloud. The mystery seemed solved. Betelgeuse would continue its variable pulsations for thousands more years before exploding. But in November 2024, Betelgeuse did something completely different. Instead of dimming, it brightened, and not just a little. The star increased in luminosity by approximately 50% over its average brightness, reaching magnitudes not observed in modern astronomical records. This wasn't a return to normal after dimming. This was something new, and it's forcing astronomers to reconsider what they thought they understood about red supergiant behavior in the final stages before supernova. Betelgeuse is a semi-regular variable star, meaning its brightness fluctuates on various timescales. The dominant cycle lasts about 400 days, during which the star pulsates, expanding and contracting as waves of pressure and heat propagate through its enormous atmosphere. At maximum expansion, the star cools slightly and dims. At maximum contraction, it heats and brightens. This pulsation is well documented and predictable within limits. Additionally, Betelgeuse shows longer period variations on timescales of years to decades, possibly driven by convection cells rising and falling in the star's interior. These variations are less regular and harder to predict. The 2019-2020 dimming was exceptional because it combined with a minimum in both the short and long cycles, amplified by the dust ejection event. The result was the dimmest Betelgeuse had appeared in recorded history. The November 2024 brightening is exceptional in the opposite direction. Betelgeuse reached apparent magnitude 0.0, rivaling Rigel, the other bright star in Orion. For context, Betelgeuse normally sits around magnitude 0.5, making it the 10th brightest star in the night sky. At magnitude 0.0, it became the 6th or 7th brightest, depending on other variables. Casual observers noticed. Orion looked different. The shoulder star was conspicuously brighter than usual, disrupting the familiar constellation pattern. Reports flooded astronomical forums and social media. What was happening? Before we examine the observations that revealed why Betelgeuse is brightening and what it might mean for the star's future, make sure you're subscribed to Cosmic Outliers and notifications are turned on. Betelgeuse remains one of the most watched stars in the sky, and we're tracking every development. Drop a comment with whether you think this brightening is related to an impending supernova or just another phase of the star's complex variability, because the data is forcing scientists to consider both possibilities seriously. Initial speculation focused on the pulsation cycles. Perhaps Betelgeuse was reaching a maximum in both its short and long period cycles simultaneously, just as the dimming had occurred at dual minima. If so, the brightening would be temporary, and the star would return to normal within months as the cycles progressed. Photometric monitoring over November and December supported this to some extent. The brightness peaked in mid-November, then began declining slowly, consistent with the star moving past a pulsation maximum. But the decline was slower than expected. By January 2025, Betelgeuse remained brighter than its long-term average, sitting around magnitude 0.2, still noticeably elevated. Spectroscopic observations provided additional clues. Spectra taken during the brightening showed changes in the star's atmosphere. Temperature measurements indicated the photosphere was hotter than normal by several hundred Kelvin. For a star with a surface temperature around 3600 Kelvin, a few hundred-degree increase is significant, potentially explaining much of the brightness increase. But what caused the temperature rise? Pulsations typically involve expansion and cooling or contraction and heating, cycles that balance over time. Sustained heating requires an energy source beyond normal pulsations. One possibility involves changes in the star's convection. Red supergiants transport energy from their cores to their surfaces through massive convection cells. vast regions of rising hot material and sinking cool material. If the convection pattern shifts, perhaps due to instabilities in the star's interior, energy transport efficiency could change. More efficient convection would deliver more energy to the surface, heating the photosphere and increasing brightness. This mechanism could operate on timescales of months to years, depending on the size and dynamics of the affected convection cells. Another possibility involves the star's mass loss. Red supergiants shed material constantly through stellar winds, losing significant fractions of their mass over time. Betelgeuse loses roughly 1 Earth mass per year through its wind. If the mass loss rate increased suddenly, it would change the density structure of the star's outer atmosphere. Lower density atmospheres are more transparent, allowing more radiation from deeper, hotter layers to escape directly. This increased transparency could manifest as brightening even if the underlying energy generation remained constant. Observations of Betelgeuse's circumstellar environment searched for evidence of enhanced mass loss, but found no clear signs of significantly increased outflow. The wind appeared relatively normal. A third, more concerning possibility involves changes in the star's core. Red supergiants, like Betelgeuse, are in advanced stages of nuclear burning. They've exhausted hydrogen in their cores and are fusing heavier elements in shells surrounding an inert core. Betelgeuse is currently fusing helium into carbon and oxygen in its core, with hydrogen fusing in a shell around that. As nuclear fuel depletes, the balance between gravitational contraction and radiation pressure shifts. The core contracts slightly, heats up, and fusion rates increase. This can trigger episodes of enhanced energy output that propagate through the star on timescales of years. If Betelgeuse's core is experiencing such an episode, the star would brighten as the extra energy reaches the surface. Core changes are particularly interesting because they're linked to the supernova process. When a massive star exhausts its nuclear fuel completely, core collapse occurs within seconds, triggering the supernova explosion. But the approach to that final moment is not necessarily smooth. The star can experience instabilities, rapid changes in energy output, and structural rearrangements in the decades or centuries before the end. Betelgeuse is estimated to be in the final 10,000 to 100,000 years of its life, a blink in astronomical terms, but still a long time by human standards. Whether this brightening represents a short-term fluctuation or a sign that the star is approaching the final phases depends on details of its interior structure that we can't directly observe. Researchers modeled Betelgeuse's interior using stellar evolution codes, sophisticated computer programs that simulate the physics of stellar structure. These models start with initial conditions, the star's mass, composition, and rotation, then evolve the star forward in time, solving equations for energy transport, nuclear reactions, and pressure balance. Models of Betelgeuse show that stars at this stage undergo irregular variability as convection and pulsation interact in complex ways. Some models predict episodes of enhanced luminosity lasting months to years, driven by convective instabilities or interactions between different burning shells. These episodes don't necessarily indicate imminent core collapse. They're part of normal, if chaotic, red supergiant evolution. However, other models suggest that rapid brightening could signal the onset of final nuclear burning stages. Specifically, if the core is beginning to fuse carbon and oxygen into heavier elements like neon and magnesium, the energy release increases dramatically but over shorter timescales. Carbon burning lasts only a few thousand years. Neon burning lasts years. Oxygen burning lasts months. Silicon burning, the final stage before core collapse, lasts days. If Betelgeuse has entered carbon burning, it would experience increased luminosity that could manifest as the observed brightening. But carbon burning doesn't immediately lead to supernova. The star would remain bright and variable for millennia. Distinguishing between these scenarios requires detailed observations over time. If the brightening is a temporary fluctuation, Betelgeuse will return to its normal variability patterns within a year or two. If it's driven by core changes, the star might settle into a new, brighter average luminosity or show continued irregular variations different from historical behavior. Long-term monitoring is essential. Fortunately, Betelgeuse is one of the most intensively observed stars precisely because of its supernova potential and variable behavior. High-resolution imaging from interferometric telescopes provided insights into Betelgeuse's surface structure during the brightening. Interferometry combines light from multiple telescopes to achieve angular resolution equivalent to a single telescope with diameter equal to the separation between instruments. For Betelgeuse, this technique resolves details on the star's surface, revealing bright spots and dark regions corresponding to convection cells and cool patches. Images taken during the November 2024 brightening showed an unusually large bright region on one hemisphere, covering roughly 30% of the visible disk. This bright spot was several hundred Kelvin hotter than surrounding areas and could account for a significant fraction of the increased luminosity. The bright spot's persistence over weeks suggested it wasn't a transient flare but a stable or slowly evolving feature. One interpretation is that it represents a massive convection cell that brought hot material to the surface and maintained it there while the cell circulated. Another interpretation suggests it could be a region where the photosphere is temporarily elevated, revealing deeper, hotter layers, or it might be related to magnetic activity. While red supergiants are not typically magnetically active like sun-like stars, they do have weak magnetic fields generated by convection. Localized magnetic activity could heat regions of the photosphere, creating bright spots. The connection between surface features and interior dynamics is complex. Convection in red supergiants operates on enormous scales. A single convection cell might be comparable in size to Earth's orbit. These cells take months or years to circulate. Observing their effects at the photosphere provides indirect information about interior processes, but interpreting those observations requires models that are still being refined. The physics of convection in such extreme environments is not fully understood. Simulations struggle with the vast range of scales involved, from nuclear reactions in the core operating on millimeter scales to convection cells spanning hundreds of millions of kilometers. As the brightening continued into December, another phenomenon emerged. Betelgeuse's spectrum showed enhanced emission lines, spectral features indicating hot gas glowing above the photosphere. Enhanced emission suggests increased mass loss or heating of the circumstellar envelope, the shell of gas surrounding the star expelled by previous winds. If energy from the brightening event is heating this material, it would glow more brightly in certain wavelengths, producing the observed emission. Alternatively, if a shock wave from the brightening propagated outward through the circumstellar envelope, it could compress and heat the gas, again producing enhanced emission. Monitoring at multiple wavelengths revealed additional complexity. In the infrared, Betelgeuse showed fluctuations indicating changes in the amount of dust surrounding the star. Dust forms when hot gas ejected by the star cools and condenses. The amount of dust varies with the star's activity. During the 2019-2020 dimming, a massive dust cloud formed, blocking visible light but glowing brightly in infrared as it absorbed starlight and re-emitted the energy at longer wavelengths. In late 2024, infrared observations suggested new dust formation, though not as extensive as the 2019 event. This dust could eventually affect the star's visible brightness if it accumulates sufficiently. The interplay between brightening, mass loss, and dust formation creates a complex feedback system. Brightening events can drive enhanced mass loss, ejecting more material into the circumstellar environment. As this material cools, it can form dust, which absorbs starlight and may temporarily dim the star from certain viewing angles. If dust formation becomes extensive, it could trigger another dimming event. Betelgeuse might be entering a phase of heightened activity where brightening and dimming events occur more frequently, driven by instabilities in the star's interior, amplified by interactions with its circumstellar environment. Historical records of Betelgeuse's brightness provide context. Observations dating back centuries show the star has always been variable, though detailed photometric data only exist for the last 100 years. Within that period, Betelgeuse has shown semi-regular variations, but nothing like the 2019 dimming or 2024 brightening. The amplitude of variability seems to be increasing. Whether this represents normal behavior at a particular stage of the star's evolution or signals something more significant is unclear. Statistical analysis of the light curve suggests that extreme events, both bright and dim, are becoming more common. This could indicate the star is approaching a transition, but transitions in red supergiant evolution can take thousands of years. Public interest in Betelgeuse has surged with each new development. The star's prominence in Orion, one of the most recognizable constellations, makes it accessible to casual observers. Unlike most astronomical phenomena that require telescopes, anyone with clear skies can see Betelgeuse and notice its brightness changes. This democratization of astronomy, where significant stellar events are visible to the naked eye, is rare and generates widespread engagement. Social media platforms have amplified this engagement, with thousands of people sharing observations, photos, and speculation. The speculation inevitably turns to supernova. Betelgeuse is a supernova candidate. When it explodes, it will be the brightest supernova visible from Earth in recorded history, rivaling the Moon in brightness and visible during daytime for weeks. The explosion will eject the star's outer layers at thousands of kilometers per second, creating a rapidly expanding nebula that will glow for centuries. The core will collapse into a neutron star or possibly a black hole, depending on Betelgeuse's exact mass. The supernova will be a spectacle unlike anything humanity has witnessed from a cosmic event. It's understandable that every unusual behavior triggers hope or fear that the supernova is imminent. But astronomical timescales are long. Imminent in stellar terms means within the next 100,000 years. Betelgeuse could explode tomorrow or in 100,000 years, and both are equally consistent with current knowledge. The brightening doesn't definitively move the needle toward imminent explosion, though it does indicate the star is active and evolving. If Betelgeuse is in carbon burning, it has thousands of years left. If it's in earlier stages, tens of thousands of years remain. Either way, we're unlikely to see the supernova in our lifetimes, statistically speaking, but the possibility is not zero. The scientific value of observing Betelgeuse's variability extends beyond predicting its supernova. Red supergiants are critical to understanding massive star evolution, stellar populations in galaxies, and the production of heavy elements. When massive stars explode, they enrich the interstellar medium with carbon, oxygen, iron, and heavier elements synthesized in their cores and during the supernova itself. These elements become raw material for new stars and planets. Understanding red supergiant behavior helps refine models of this chemical enrichment process, which affects galactic evolution and planet formation. Betelgeuse is also close enough to study in detail. At roughly 500 to 600 light-years distance, it's one of the nearest red supergiants. Most are thousands of light-years away, too distant for detailed surface imaging or precise spectroscopy. Betelgeuse serves as a laboratory for studying red supergiant physics. Insights gained from observing Betelgeuse apply to understanding red supergiants throughout the universe. Every new behavior observed, every brightening or dimming event, refines theoretical models and improves our ability to interpret observations of more distant stars. The brightening also sparked discussions about predictive capabilities. Can we predict when Betelgeuse will explode based on its behavior? The short answer is no. Supernova precursors are not well understood. We have theoretical predictions about what might happen in the final years, months, or days before core collapse. But we've never observed a star closely enough in those final stages to test the predictions. The only supernova precursor star observed with modern instruments was the progenitor of SN 1987A, and that was a blue supergiant, not a red one. Its behavior before explosion didn't follow predictions based on red supergiant models. Betelgeuse might show precursor signs, or it might explode with no warning. We don't know. Advanced neutrino detectors might provide a few hours warning. Core collapse generates a neutrino burst that precedes the visible explosion by hours, as neutrinos escape the collapsing core faster than photons. Detectors like IceCube in Antarctica or Superchemiocandi in Japan could detect this neutrino burst if Betelgeuse explodes within our galaxy. This would give astronomers time to point telescopes at Betelgeuse to catch the explosion as it happens, a unique opportunity to observe the earliest phases of a supernova. But neutrino detection provides warning only after core collapse begins, too late to predict based on earlier behavior. Monitoring programs continue. Multiple observatories track Betelgeuse's brightness nightly. Spectroscopic campaigns obtain regular spectra. Interferometric facilities image the surface when weather permits. Space telescopes monitor in wavelengths inaccessible from ground, ultraviolet and infrared bands that reveal different aspects of the star's behavior. This comprehensive monitoring ensures that any changes are documented immediately. If Betelgeuse enters a truly unusual state, scientists will know and can mobilize resources for intensive study. The societal impact of a Betelgeuse supernova would be significant. Beyond the scientific windfall, the visual spectacle would affect culture. A new star rivaling the moon in brightness would dominate the night sky for weeks. then slowly fade over months to years. Ancient cultures would have interpreted it as a profound omen. Modern society would see it as a cosmic event, something to document and remember. It would inspire art, literature, and music. It would drive public interest in astronomy to unprecedented levels. And it would remind humanity of the dynamic, violent nature of the cosmos, that even familiar stars and familiar constellations are temporary. But for now, Betelgeuse remains in its red supergiant phase, variable and unpredictable, but not exploding. The November 2024 brightening has subsided somewhat, though the star remains above its long-term average. Whether this represents a new baseline or a temporary fluctuation will become clear over the next year. If Betelgeuse settles back to historical norms, the brightening was just another episode in the star's ongoing variability. If it remains elevated or shows continued unusual behavior, it might indicate a genuine shift in the star's evolutionary state, a transition that could play out over decades or centuries, but marks progress toward the eventual supernova. Theorists are updating models based on the new observations. The combination of the 2019 dimming and 2024 brightening provides valuable constraints. Models must reproduce both events, explaining how a star can undergo such dramatic variability. This constrains parameters like convection efficiency, mass loss rates, and interior structure. Improved models will make better predictions about red supergiant behavior generally, not just for Betelgeuse. Those predictions will inform interpretations of observations of distant red supergiants in other galaxies, helping understand stellar populations and chemical evolution. The emotional connection people feel to Betelgeuse is interesting. It's a star, a ball of plasma undergoing nuclear fusion, indifferent to observation. Yet because it's visible and prominent, it becomes personal. Sky watchers who notice its brightness changes feel connected to a cosmic event spanning light years and millions of years. This connection drives amateur contributions to astronomy. Citizen scientists monitoring Betelgeuse report observations to professional databases, adding data points that help characterize variability. This collaboration between professional and amateur astronomers is a strength of modern observational astronomy, enabled by accessible technology and internet communication. The possibility that we're living during Betelgeuse's final millennium or century is tantalizing. Humans have existed as a species for roughly 300,000 years. Recorded history spans about 5,000 years. If Betelgeuse explodes in the next 1,000 years, we're living in the narrow window when this particular star ends its life. That's statistically unlikely, but not impossible. And if it happens, it will be the most significant astronomical event in human history, visible without instruments, affecting everyone who looks up at the night sky. The anticipation builds with each unusual behavior, each dimming or brightening, even though we know the odds remain long that it happens in our lifetimes. As observations continue, patterns may emerge. Perhaps brightening events like this one occur regularly on timescales of decades. Historical data might reveal previous episodes that weren't recognized as significant. Or perhaps this is genuinely new, the first time Betelgeuse has done something like this in millennia. Distinguishing between these possibilities requires patience and continued vigilance. Astronomy is often about waiting, watching, and accumulating data slowly. Betelgeuse rewards that patience by being endlessly interesting. If this deep dive into Betelgeuse's latest unexpected behavior captured your fascination, hit that like button and subscribe to Cosmic Outliers for immediate updates on the star's ongoing saga. We're monitoring Betelgeuse constantly and will report any new developments as they happen. Drop a comment with your prediction. Will Betelgeuse explode in your lifetime, or will it continue teasing us with variability for thousands of years more? This is one of the most dynamic stars we can observe, and its story is far from over.